go. So I've done the solve. Shell XT identifies the atom types. Now in this one, it's similar to what we did in maybe last lecture. It was an N oxide. And so it correctly identified the nitrogen and oxygen. But you may ask, well, how do I know this one here is an oxygen versus this one where it's carbon? And what we'll notice when we do the electron density map is you'll see 3 peaks off of this carbon and no peaks off of this carbon, off this oxygen. So that those 3 peaks off the carbon signify hydrogen atoms, whereas no peaks off of this oxygen signifies it can't be a carbon, because you can't have a carbon with no hydrogens if it's a terminal carbon. In addition to the molecule, we have 2 additional electron density peaks that they've labeled as, identified as oxygen molecules. And so since they're in the crystal lattice, these are what we call solvent molecules. So in this, either the reaction conditions or the solvent, the crystallization solvent, somewhere water played, or water got into the lattice, either by reaction conditions or by the crystallization solvents. I'm just going to quickly label the atoms. Now, this is a good one. Not always are the water molecules easy to model. Sometimes they're a bit disordered, and it makes it a little bit more complicated. Okay. So we're going to go to refine. We use Shell Excel. And so you see most of the, or actually all of the remaining Q peaks correspond to hydrogen atoms on the in the crystal lattice. And so at this point, what we're going to do is we're going to do anisotropic thermal parameters for the non-hydrogen atoms. So we're going to click on this ellipsoid here, and it'll automatically convert it to anisotropic. If we increase the number of peaks, say to 20, and we refine, you'll see that all the remaining Q peaks correlate to hydrogen atoms. And you'll notice on this carbon atom here, you see that there are 3 Q peaks, signifying that there are 3 hydrogens located off this carbon. Whereas you look at this oxygen here, there's no Q peaks. So that it signifies there's no hydrogens off of this oxygen atom. And so that kind of confirms that this is an oxygen, and this is going to be a methyl. And so now we can click Add H. And so it's kind of interesting, the people who were here earlier before my Wi-Fi dropped, when we did Add H, it actually calculated the hydrogen slightly different on the water molecules, if you remember. So now you'll see that these 2 hydrogens are kind of running into each other. So there's a hydrogen on one water molecule, hydrogen bonding with this one, and there's a hydrogen on that one, hydrogen bonding on this one. And this you can't have. You can't have 2 hydrogens hydrogen bonding like this. One has to be an acceptor, one has to be a donor. So in this case, it didn't do a good job at finding all of the calculated position, or calculating the hydrogen atoms on the water molecules. So we're going to use electron density map to determine this. It did an okay job for some of them, but for these 2 here, one of these is not right. So it's either this one or this one needs to be changed. And so what I'm going to do is I'm going to delete the hydrogens. And typically on the oxygen atom, typically with water molecules, you want to determine the hydrogen atoms using electron density map anyways for better, better hydrogen bond distances. So then we hit refine again. And you'll notice now we have a few peaks off the water molecules. You want to look at the ones that are the darker shaded brown. That means they contain more electron density. So here we have these two peaks. If you right click and bang, you see that this one's about 0.85 angstroms from the oxygen. And this one is about, where is it? 0.73. So that one's a little short, but it might refine itself a little better. So we're going to add these as hydrogens. And down here, we're going to add these two darker shaded electron density peaks as hydrogens as well. And see what happens. Then we click refine. So at this point, we can check to see if this hydrogen-hydrogen bonds is something. So we go to Bang Explore, and you see here it hydrogen bonds with an oxygen that's about 2.185 angstroms away. So this hydrogen is located in the right position. Now if we look over here though, this other hydrogen that's labeled H3A, if we right click, just bang, look at its bond distance, it's a pretty short oxygen hydrogen bond. It's H3A to O3 is 0.714. Typically these are about 0.85 angstroms roughly in that area. It can be 0.85 to 0.95, even 1, but this is a little bit short. So what we're going to do here is we're going to try to restrain this bond to make it a little bit longer. So that way it won't bond with a neighboring hydrogen here. So this is not acceptable, this little bond between the two hydrogens. And the reason this happens is because this bond is really short. So if we lengthen this bond here, this won't happen, this connection. So we're going to add a restraint to this hydrogen bond. And we'll just check this one as well. So that one's about 0.95. So what you do is you click on the two atoms you want to restrain. So we want, or the bond you want to restrain. So we click on the hydrogen and the oxygen. And we go to Tools. And we go to Restraints. And it's called Defix. And then you type in what you want to restrain it to. We'll say 0.85. And you hit go. So now when we refine it again, it's going to refine it where it's going to restrain that bond length to that value that we gave it. Secondly, we need to convert these to the UISO. You right click, UISO needs to be 1.5. Right now it won't do it to us. Let's do a grow, fuse. Still won't let us. Let's see. There, we can do that one. Not that one. Not that one yet. So let's see. So it won't let us do it yet, so we'll do a refine. And now that one bond should lengthen. So now you see that if we check now, it increased a little bit to 0.762 angstroms. But you see here that there's an electron density peak located here. And this is what you do when you're trying to find hydrogens on water. You try to see what gives you the best looking hydrogen bonds. So here we have an electron density peak. It's about 0.94 off of this oxygen. That's 0.93. So what I'm going to do is I'm going to delete this one and this one. And we're going to label this one a hydrogen. So now when I refine, so see how it moved it. Again, it got rid of it. It didn't like it being there. So now we come here, relabel this one hydrogen. Bang. This is pretty short, so we're going to put a defix. And the reason you need to make them a little bit longer is because when you do a check if it'll say, hey, this is a pretty short bond. You need to explain why. So here it's still not giving us any reliable result. So what I'm going to do now is try a different restraint. And I'm going to restrain it to the hydrogen bonds here. So what we can do is if we do a bond, we create a bond, I can see how long this bond is by doing a bang. And it's 2.0 angstroms. So then I come here, remove that bond, and now I'm going to restrain this distance here so that it keeps this hydrogen in this location. So we're going to come here, tools, defix, I'm going to restrain it to 2.01. Now you'll know when the hydrogens are unhappy because your shift parameter will never converge. So we hit refine. Bang. And so you can come to edit and we can shorten it if we want. I'm going to shorten it to 1.95. Okay. Alrighty. Let's see. So at this point, I'm going to leave the hydrogens where they are, just kind of help fix the distances by adding restraints. Again, oxygen hydrogen bond can go anywhere from about 0.8 to 1, depending on what's its hydrogen bond to. So you see here the shift is still not converging. So what that tells us is that there's some hydrogen here that's not happy. So if we delete this hydrogen and refine it, so it wasn't that hydrogen that was unhappy. Let's delete this one, refine. So as you can see, those two hydrogens are making this unhappy. So we need to try to remodel this a little bit better. So then you can come back and we can try to do the add hydrogens again. So we come down here. So this one did a little bit better job of adding the hydrogen. See, now we don't have that two hydrogens running into each other, and you also notice that the hydrogens that we calculated fall on these electron density peaks. So these line up quite well. And so now we'll do a refine. And you see now it's convergence. So what happens is the difference to doing calculated versus using electron density peaks is with the calculated, it already constrains the hydrogen bond distances. So if I click on it, it's going to have it set to a default value, which is 0.85. And this one's also going to be 0.85. So sometimes the calculated works better than the experimental. Sometimes it's the opposite. You just have to play around to see what works. And in this case, when we did it again, the calculated, it worked better than it did the first time. So now if we just check, we got to check that each hydrogen bonds with something. So we explore the hydrogen. You see that there's a hydrogen bond with another oxygen that's about 2 angstroms away. And then if we check this one, there's another oxygen about 1.95 angstroms away. So those are in good positions. If there was no oxygen or nitrogen around, that would cause an error in your check CIF. So now as far as structure solution, this is good so far. Now we have to work on the technical things. So if we look at our percent, we can see if there's anything out of the ordinary. This looks pretty good, linear data, so that's all right. Again, you just click on the percent sign for that. We go to info, we go to bad reflections, we can check, and currently there's no reflection that needs to be removed, and as we saw on the graph, none of them look out of that linear plot, so that's good. And then we go to the reflection statistics. We're going to go to the I over sigma versus resolution. And so here's where you'll know where we have bad data and good data. So again, the minimum 2 theta cutoff for molybdenum radiation is 50 degrees. Anything below 3 sigma can be removed. So you see here about 66, 67 degrees 2 theta. This data here is in the noise area. So we don't even know if it's real data or it could be extremely weak data. So, you know, we can delete. It'd be okay to delete above 65 degrees 2 theta, but since 50 is our minimum, I usually set it to about 55 degrees 2 theta. Because generally the higher the I over sigma is, the better quality data you have. And this I over sigma here for this one is about 5. And so 10 is usually the minimum threshold for good data. So we're going to set it, the cutoff, to 55 degrees 2 theta. And that's a good starting point. And then if you need to, you can cut off more up into 50 degrees. So what we do is we go to edit, instructions, and then somewhere in the second set of instructions, you're just going to go space, omit, -3, 55. And for molybdenum radiation, this is very common, but for copper, typically your high angle data is very well diffracting, and so you won't have to omit as much data as you would if you were collecting data on molybdenum radiation. So now we're going to refine again, and this should drop because we're getting rid of all that weak bad data, high angle data, and so this should help our R factor as well. And so you see here the R1 dropped to about 5.2. The weighted R2 dropped to about 16.2, so a significant drop because we got rid of all that extra, not extra, but all that weak bad data that may not even be data, it could just be noise. So that's good. Now if we go back to info, we check our bad reflections, still nothing pops up. So the last thing we need to do is adjust the weighting parameter. So since our proposed adjustment is 0.088 and 0.054, I'm going to go ahead and use the recommended adjustment. So I click on that, it turns green. I hit refine. Now here, I don't like what it's recommending, so I'm just going to go to edit instructions, and I'm going to manually change it to what I want it to change it to. So say 0.06 and 0.15. And so here we're spot on 4.95%, 13% R2. Everything is a shade of green. Now this D min is at 0.77. That's because we set it to 55 degrees 2 theta. If you wanted to try to get it green, you could even have a lower cutoff of 2 theta of say 50 degrees, and it may give it green, it may not. But light green is okay. As far as completeness, you really can't do anything with this unless you recollect data and collect more data. Maybe you didn't collect enough data when you did the data solution. So now we go to report. Let's see, crystal. Let me see if I have the data for this. So I didn't right, but we'll just put the majority of these crystals I get are colorless anyway, so. Multi-scan is the absorption type. Now the Tmin and Tmax you can get from the crystalclear.cif. Tmax is typically 1. For diffraction, we got to set the temperatures. And then we're going to go to edit CIF info because we're going to add that extra information that never gets copied over. And that's the cell measurement reflections used. And the cell theta min, theta max. And then the device type. All right, that just saves us from having to do this stuff again. And if you put it in the edit CIF info, it automatically keeps it and updates your CIF file. So now we're ready to do our check CIF. Click on the check CIF button. Hopefully it works. And then after this, I'll stop, take questions, and then I'm going to continue with this structure. I'm going to show you a different way you can address solvents in the crystal lattice. And you're going to think it's a little bit of a cheating what you do, but you can do it sometimes if it's difficult to model the solvent. So let me bring up the check SIF so we can take a look at it. So here we have our check SIF. Everything looks good. It's all in agreement. We look down here. We don't have any check SIF A or B errors. And the typical A or B error you may encounter when dealing with water molecules, excuse me, is either the hydrogen bond that you found on a water molecule or the hydrogen you found on a water molecule doesn't hydrogen bond with a neighboring water molecule or somewhere on the molecule. And so that's a red error, and you have to either explain it or you have to go and try to find a different position for the hydrogen so that it finds something to donate or to hydrogen bond with. The second thing you can encounter is the OH bond is either too short or too long. Then you have to put in those restraints that I mentioned so that you can either elongate it or cause it to decrease. But whenever you do the HAD and it calculates those hydrogens, you don't have to worry about that because it sets it to a fixed distance, so that's okay. So that's one of the advantages of using the calculator is you don't have to worry about the hydrogen moving too much because it's constrained to that whatever that distance is for the OH bond. So this is pretty good. There's nothing we need to change about it. So let me go back to the OLEX. And so just a few things I want to show you. If we look at the packing, so we do a pack. And let's say we look down the A-axis, MATR1. What you're seeing here is you see these kind of channels of water, or these channels that have these hydrogen bond waters in it. So this is looking down the A-axis. If we look down the B-axis, MATR2, you see here's where we see this. It's kind of like a hydrogen bond ring or chain. See here? And it's going down the B-axis. So let me see if MATR3, we look down the C-axis. So we rotate it. You see that each, I guess, molecule is connected to another one in a kind of a channel through this hydrogen bonding of the water. So these waters form these water channels that the water hydrogen bonds as it crystallizes in the lattice. So that's what you're seeing here is these hydrogen bond channels which are propagated down the, I think it's the C-axis, let's see. Oh, down the A-axis actually. So when you're doing your X-ray, your description of the X-ray structure, you could, one thing that might be important is you could say that these water hydrogen bonded water molecules form a channel down the A-axis. So that's something interesting for this structure. So again, you use the command pack. MATR1 looks down the A-axis, MATR space 2 looks down the B, and MATR space 3 looks down the C. And those commands are from old school ShellX from back in the day when you had to type in the commands. So I'm going to finish with this structure solution here, take any questions, and I'm going to continue and show you a different way to address solvent molecules. So let me stop the share.